Hi everybody, so in this video I want to introduce two groups. Over here we have the alkali metals, and then over here in group 2 we have the alkaline earths. Now all of the elements that occur in these two columns share very similar kinds of characteristics. Let me just rewrite that. That should be the word alkaline. So to understand how the elements in these two groups operate, we're going to look at how we write electronic structure. So remember that we're filling in sequentially the KLM shells or the first, second, and third quantum numbers that represent those shells. So in this diagram, what we're going to do is we're going to start with neon. How would we write the electronic structure of neon? Well, to get to neon, we need to add, we're going to fill the K shell. We're going to add 2 electrons here. The K shell, that's the first shell, so we'll just use the number. It has an s orbital only. There's 2 electrons that go in it, and we'd call it 1s2. Then we're going to fill the L shell, which is the second shell. And for that second shell, we're going to fill in both of the electron positions in the s orbital, and then we're going to fill in all 6 electrons that'll fit into the p. So we can write that as 1s2, 2s2, and p6. And you can add another 2 in here. Some people do, some people don't. Put 2p6 if you want to be extra careful about specifying that those p electrons are in the second shell. So now let's say we want to look at an element like magnesium. So magnesium has 12 protons in its nucleus. It can pull in 12 electrons. We don't want to write this entire notation. We're going to let neon in square brackets count for all of this. So to get to magnesium, we would write magnesium as this. We'll use neon as a shorthand for the first 10 electrons that are going to fill into the lower energy levels in magnesium, and then add all the stuff that comes after neon. So after neon, what do we have? We have the 3s2, a little bit dyslexic here, the 3s2, and then that's it. It's done at 3s2. So this would be the the electron notation for magnesium. How about sodium? Let's take a look at sodium. Sodium would be very similar. We can again use the neon shorthand. It's neon in square brackets, but it's only got 1 electron in that 3s orbital, and so we'll write it as 3s1. Now, the reason why this part is interesting and important is because we've got this guy over here, oxygen. Now remember, oxygen is the single most abundant atom in both the crust and the mantle. And oxygen, to get to the neon gas state, all it has to do is add 2 electrons. Right here, it's sitting out in the 2 what? Let's write out the electron structure for oxygen. For the oxygen atom, oxygen would be, it would be helium in square brackets, and then after helium, we're going to fill in the 2s2, and then the 2p, and how many p electrons? 1, 2, 3, 4, so the 2p4. So if oxygen can just simply add 2 more electrons to get up to 2p6, then it would look like neon in terms of its electronic configuration. So why does that mean anything? Well, if oxygen is able to pick up 2 electrons from another atom that doesn't want 2 electrons, then they can bond together. So if we take a look at magnesium here, Magnesium had those 3s2 electrons sitting in its outermost orbital. It's happy to get rid of those. By getting rid of those, it gets to a neon noble gas state also. So it's happy to donate those 2 electrons to oxygen, and you end up with compounds like Mg. Oh, 1 magnesium and 1 oxygen are happy to bond to one another. But here's the beautiful thing about the periodic chart. That's going to be true for everything in this second column. All of the alkaline earths will have this common characteristic, whether it's beryllium, magnesium, calcium, strontium, barium. They're all going to have these 2 s orbital electrons sitting out there just waiting for an anion like oxygen to pick them up. So it's very common for these guys. Well, they almost always invariably have a 2+ charge. And it's the same idea for the alkali metals. Whether it's lithium, sodium, potassium, rubidium, etc., they all have that 1 electron sitting out in the s orbital. They're happy to get rid of it and attain a 1+ charge. And so that means that these guys all react very, very similarly to one another when they're bonding with anions or other kinds of atoms. And so that's why they're grouped together. That's another part of the beauty of the periodic chart, that we have things like the group of elements out here, the noble gases or the transition metals, etc., that have these common characteristics and allow us to make predictions, very powerful predictions about how things will react, or when we're studying geology or environmental sciences, where we would expect different kinds of elements and how we would expect them to be